Okay, so this little video is basically how is it that we actually check for something being prime? So one of the other videos before this talked about the sieve of Eratosthenes. And if you remember, we wrote down sort of a grid of numbers. I did up to 108, and sort of we walked through, and after the procedure, you kind of have a list of primes, a list of the primes. But the trouble is now, what if we have something larger? Like I have the number, let's say, so let's say 293 prime. And one thing you could do is you could go, all right, I could go back to the sieve and write down all the numbers up to something above this, maybe to 300, and do the same thing, right? And you could go through and then that would give you a list up to that, and if that was on the list, it would be prime. May not be so practical as things get a little bit larger. What if I wanted to test if the number 997 was prime? I don't know, is it prime? It's hard to say. So we're going to talk about that. The big thing about this, so we'll actually check this one in a little bit. This little theorem is called the primality test. So a whole number is prime unless it has a prime factor p less than the square root of n. That is to check, let's use check instead, to check for primality, whether or not it's prime, of n, test divisibility by 2, 3, 5, p, where p squared is less than n. Okay. So we got that. So basically the thing about it is, what is it that we need to check? So I'm going back to this example. What is it that I need to check? So I could check like all numbers, because again, definition of prime would be the only two factors are one in itself. So I could check 2, I could check 3, I could check 4, all the way up to 292. But basically what this is saying is that's unnecessary. The only way it would be prime is if it had a prime factor p less than the square root of itself. And so let's go ahead and prove this, and then we're going to use it a little bit later. So first of all, I'm going to write capital N as P times K. I'm losing my notes here. P is prime by smallest factor theorem. This was one we did a few videos ago, where basically I can always write n as the product of a prime and something else. So the smallest factor is always prime. And p is less than or equal to n. Sorry, capital N. No, sorry, p is less than k. My bad. Okay. Okay. Right. So you write it in order. You can even say we're starting the proof. Multiply by p to get p squared is less than equal to kp, which is n, right? And that's our relationship that we tried to set up. Okay. So, all right. So again, I'm not worried too much. The thing I want you to take away from this with these little proofs are sometimes that they're not too difficult to do. You start to see kind of the structure of them. Also how things build on each other, right? We're using these other little theorems to build up other things. But one thing that we're going to want to do is walk away from this and figure out how to use this. So I'm going to go back to this. All right. So what we're going to do is this stuff down here. Is I'm going to start by I'm going to walk through all of the primes up to that. So, and I think, is this the one I want to start with? Let's start with a little smaller one, and then we'll come back to this. Okay, so is 203 prime. Okay, one of the things that is going to be kind of helpful with is knowing some of the so I'm going to write down our primes here. Let me just start with those. Let me call this label P and P squared, right? 4, 9, 25, 49, 81, 121, 289. I have to look up these other ones again. 13, sorry, 13 squared, 169 of course, and 19 is 361. Okay. Okay. So what we're going to do is, if I've got a list of these things, then you kind of look at, right, I need to go to 13. Because after that, right, the square of that is bigger than the number itself. So remember, I'm going to walk through all of the, so we test all prime p up to p squared less than, I would say 4 p squared less than n. Right, so that's up to 13. Okay. So divisible by 2. Right? Now this is where our a bunch of our tests are going to be helpful. Right? It's not even, so that's a no. By 3, right? Sum the digits, no. By 5, right? That's not a 5 or a 0, so no. By 7. Okay. So this is one of these that there's a couple things you could do. So there's no there's no nice test for 7. There are some ones, but it's not very easy. It's useful for very large numbers, but not these small numbers. So there's a couple ways of going about doing this. So one, you can always just do some long division to test that. I always like the divisibility lemma, right? So I'll show you both of those and see this. So I'm going to look at, let's just do the 7203, right? So 14, and that's a 9. So 63, 0. Okay. So that means this was a yes. Therefore, 203 is not prime. All right, the other thing that I would often do, and this I could say a little bit of mental math for this kind of level of stuff, is that something close to this that is divisible by 7 is 210. Right, 210 we know, so that's again on the divisibility lemma, that's the known fact. And then what we're going to do is we're going to test that difference. The difference between 210 and 203 is 7. Since 7 is divisible by 7, then 203 is divisible by 7. So then that's what I would get there. Okay, so that's some little mental math you can do with that. Okay, well, now let's go back to 293. So 293 prime. Okay. So is it divisible by 2? And the answer is no. 3. So I'm going to add digits. Well, there's 12, 14, so that's a no. 5, no. 7. So I'm going to try the divisibility again to see if we can do that. So I know that 280, which is pretty close to that, is divisible by 7. So that's my known fact. The difference is 13. 13 is not divisible by 7. So that's not divisible by 7. So no. Okay. I don't know why I put 9 up here. That's not a prime number. I'm sure somebody in there was checking me and said, what are you doing? 11. Okay, 11 again. The sum of these digits is 5 minus 9 is negative 4. So that's a no. Okay. We need to go up to 17 though, right? So 13. All right. So 13, this is going to be one of these that perhaps a little bit tricky. I could do something close to this that's a multiple of 13 is 260. The difference is 33. 33 is not divisible by that. All right. So again, I wrote this as, let me do some scratch paper, 293 is 260 plus 33, right? That's divisible by 13 because it's that times 20. That's not divisible by 13. Right. Okay, 17. That might be a little bit tricky too. We could take 340. The difference is 47. And I believe that's a no. Let's check this one with some long division. Just to double check. Right. And in case, you can always do this to just double check. 123. Okay, now we got to figure out some multiples of 17. Let's see. 5 it looks like is too big to me. No, 5's not too big. 6. It might be either 6 or 7. I'm gonna guess that's gonna be 6. 6 times 2 is 42. 102. And so that wasn't big enough because this was because that was bigger than that. So 7. 7 is 9. 49. Right. 7 and 7 is 7 times 1 is 7 plus 4 is 11. 4, right? Okay. So that's a no. Okay, the point of this though is I can stop at 17? So the answer is yes, 293 is prime. Okay. So you can actually do this with some fairly big numbers even by hand fairly easily. Knowing some of this stuff is nice, and kind of, you know, maybe the next couple is about all you typically need to know. The next one is 23. 23 and 29 are the next two primes. Give you some ideas of, you know, even if it's a bigger number, you probably just need to check a couple more like this. So, okay, so that wraps up the test for primality.